Hello everyone. Well, in fact, I did this one on Zoom earlier in the morning. Nobody joined though, but however, I failed to record it. I don't know what happened over there. Okay. Anyhow, I got just all the error message, and then I didn't get the recording. That's why I'm redoing it. I'm sorry. Okay. I think the demand is so high. I don't know. It may come back later, many hours later. Okay, but it's too late, so that's why I just decided to do it again. All right. So anyhow, I received a question about this. So if log x to base 7 is a and log y to base 7 is b, then how would you like to rewrite this? Well, this, because we can write this one as x cubed plus, yes, we can split into two different logarithms. So 5th root of y, and this is what, 3 times log x to base 7, and this is 1/5 power, correct? Y to the 1/5 power, so therefore you can say 1/5 and log y to base 7. Once you write it this way, yes, we can say that this is a 3a plus 1/5 times b. Okay, this is going to be pretty common case for just to check your knowledge of how to rewrite things. Alright, so for today's lecture, I'm not going to take a full class period, but I'm going to start from example 4. Okay, so this is a core of this. Today's lecture is about this law is exponential growth and decay model. So what I mean over here is that, well, we saw a couple of weeks ago f of x equals 2 to the x versus g of x equals 1/2 to the x. What was the difference? Do you remember that? F of 2 to the x is increasing like this. On the other hand, g of x is decreasing like this. So this is g of x. Therefore, this growth model is this, and the decay model is this blue curve. Well, can you rewrite this 1/2 to the x power? We can say that this is 2 to the negative 1, because 1/2 is 2 to the negative 1 to the x power. Therefore, is 2 to the negative x. Yeah, so now we can write that g of x equals 2 to the negative x. Therefore, our model is basically y equals 2 to the x versus y equals 2 to the negative x. So when you have a negative exponent, it will show you the decay is positive, is going to be growth. So our models are like, well, when you deposit money in the bank, money will grow, okay, based on the interest rate and the number of years that you are going to leave that in the account, correct? Okay, so the money growth. Well, human population grows. Or what even some in biology lab that, the fruit flies can multiply quickly. So then they show also exponential growth. So those things I will do first. Okay? So you can see, depending on the book, you can see y equals y naught e to the kt. Or f equals p times e to the rt. Okay, or y equals c times e to the rt. They all look alike. What is in common is that some outcome is some constant. Okay, here on the y naught on the k, these are constant. And here constant is p and r are constant, and here c and r are constant. And what is a variable? Variable is just p. Variable is t. And you are going to read this one carefully. T could be in terms of years, or in terms of minutes, or even in seconds. You see all those the projectile problems, their t variable was in seconds. Okay. So having said that, so what is in common? So let's plug in t equals 0 in all these places. What you get? When you plug in t equals 0, this is going to be 0, e to the 0. So y equals y naught times e to the 0, which is 1, so y naught. Here f equals, same thing, p. Okay? Here y equals c. So what do you call these constant? Either you call it y naught. By the way, y naught is y naught. So it's basically you call it y0. Well, y equals c. So t equals 0, meaning no time has passed. So you can say this y naught, or y naught and p and c, we can call this initial amount. So initial amount could be dollar amount, okay? Could be in dollars, or could be in counting, okay? Some number of human beings. Yes, those things are this. So the very first one in example 4 is this, okay? This is just basically the way they write, okay? When these authors write that, it doesn't carry their kind of what they mean. Here, when you see f, f is for future value. When you put the money in the bank, money will grow. So in future, so in 2 years, your money will become this amount. In 5 years, this amount, okay? On the other hand, the P is, present value. On the other hand, there is more common name for that. That is called principal. It's like a school principal, okay? Principal. So whether you deposit money or invest money or you borrow money to buy a car, whatever you want to do, it is going to be same under the same formula, okay? And R is interest rate. And the T is going to be time in years. Yeah, not months or days, okay? And the P is this, okay? When do we use this formula? We use the word, the interest is compounded or accumulated, okay, continuously. Oh, sounds very good, right? Yeah, your money is compounded continuously. Well, the interest rate is for example, let's say 10% per year. They want to chop this 10% into very, very small portions, but they keep updating. That means they are going to keep adding your interest to you. So if you see the words here, your interest is compounded continuously, you can use this formula. Okay, so example 4, what do we have? How long will it take for the money in an account that accrues interest at a rate of 4.25%, meaning R equals 4.25%, compounded continuously? You see the words, okay? To double. So, the big picture is that you start with the principal P, okay? You don't know how many years it's going to take. Well, this money will double. So, this is going to be what? You can say 2P. Is that right? Okay? Under what condition? 4.25% compounded continuously. Okay? So, how we are going to find the T? Well, let's look at the more concrete scenario. So, modest investment. You invest $100 and you wait until it becomes $200, you have $200 in your account. Let's look at some big businessmen. Businessman or businesswoman, okay, invest $5 million in account and wait until it becomes what? $10 million. Will it take the same amount of time or at different times? Well, it is a lot more money, so it may take a longer time than this, but we'll see. So our equation we are going to use is F equals P times E to the RT. So let's see. F, future. In the future, you want to have $200. Okay, right now you have $100. E to the R interest rate is 0.4. I'm sorry, not 0.4. 0.0425 times T. We don't know. T is. We solve this equation and find the T. Okay? The other one is, yes, we want to have $10 million. So $10 million equals $5 million times E to the RT. So same interest rate we are going to apply. Okay, so 0.0425 times T. So let's see what happens. Well, we want to find the value of T, but what do we do first? Yeah, we are going to divide both sides by 100. Okay, so 100, so that gives you 2 equals 2 e to the 0.0425 t. How do you solve this equation? Yes, so let's now talk about your future. If you take business calculus because you want to go to business school, study some finance or accounting stuff, okay? Yes, you are going to see this problem, a very, very popular problem in finance area, okay? So when you solve this, what do? Well, e to the sum time equals 2. Yes, you need conversion, okay? So conversion, so that is log and the same base e, and we are going to switch the side, right? So log 2 to base e equals 0.0425 t. So what do you call this? Log 2 base 2. That is ln 2. Okay? ln 2. So see what happens over here. T equals ln 2 divided by 0.0425. Okay. Just leave it alone and let's go over here. What happens? Well, we are going to set up an equation like this. So 10 million equals 5 million times e to the, over here, I already said that. Okay. Now what do? We divide both sides by 5 million. So this cancels. Guess what? What's left over here on the left? 10 million divided by 5 million, therefore this is 2. So what's left? 2 equals e to the 0.0425 t. What I'm showing over here, this is the same as the equation we saw earlier here. So what it says over here, it doesn't matter from $1 to $2, or from $100 to $200, or from $5 million to $10 million. If you are waiting for your money to double, you are going to wait for the same time, same amount of time, okay, in years over here. So let's compute. Pick up your calculator, and that gives you ln 2 divided by 0.0425. That is 16.31 years. So in other words, it's a long time, isn't that right? Okay? So here is now the mystery is solved. You wait for 16.31 years, so roughly 16 years and 4 months, okay? And then your money, this unspecified money, P dollars, will become 2 times P dollars. Isn't it interesting? I thought this is a very interesting case. Okay, so This is when you see money, P and the F, those things you are going to see that. Okay. Next. Next case is example 5. Determining an exponential function to model population growth. Yes, I think this is a population growth. Yes. According to the U.S. Census Bureau, the world population reached 6 billion in during 1999. And then 2010, what is the population? 6.947 billion. And the projected world population in billions of people, T years after 2010, the model is this: f of t equals 6.947 times e to the 0.00745 t. Yeah, you have the same flavor of this money problem, right? So let's say this is $6,900 or $10 million. E to this, the increasing rate over here, okay? Increasing rate and the time. So, well, the UN can have a different model. The US Census Bureau, so basically US government can have a different model. Another countries, so for example, United Kingdom can have their own model. Well, so they have, this is our model you are going to see and answer the questions. What will the world population be at the end of 2015? So, by the end of 2015. So what is that? That means 5 years after 2010. So t equals 5. So timeline is given. In that case, all you need is output, correct? You need is output, so just plug in, that's all you need. So f of 5 equals 6.947 times, when I see a lot of decimals, I use just parentheses for everything. 0.00745 and then times 5 over here. Okay? Put in a calculator and that gives you 7.211 billion. Okay, so this is what we can use for this with this model. So B is a more interesting case. In what year will the population reach 8 billion? So, in other words, f of t equals 8 billion, and of course what? What is the value of t? Okay? Yes. What is the value of t? So how we are going to compute that? F of t is 8 billion, so go over here, put 80 here. 8 billion, and we are going to solve for t. Is that right? Okay. So our population, the whole human population, did it reach 8 billion? Not yet. Okay? Not yet. So let's see over here how we are going to do it. Well, whether that is complicated or not, yes, you are going to divide both sides by 6.947. Divided by 6.947. So this, so what is that? 8 divided by this is 1.152. Okay, 1.1512. Okay, 12. So now we solve this equation. 1.1512 equals e to the 0.00745 t. we are going to solve this one. So what do? Same as before, okay? Again, is this simple numbers or complex numbers, doesn't matter. What you have is an exponential function, and there's no other exponential thing over here, therefore we are going to convert. So what is that again? ln, because this base is this. So ln 1.1512 equals this. Okay, so what is t? T equals, okay, from here we are going to go up. T equals ln 1.15212 over this number 0.00745. Yes, what do you get? That is roughly 19. Okay, so what does that mean? T equals 19, but T is what? Number of years after 2010. So what is year? Is 2010 plus 19, that is 2029. This is a projected year that human population will reach 8 billion. Well, how accurate is this model? I mean, in terms of a calculation, this is what we can do, okay? But now, when you make a model, of course, the value of this model is how accurate is it? Well, right now, what is the human population? Right now, we have 7.8 billions. So still how many years left? 9 years left. So what does it tell you? This growth was not fast enough, okay? Very soon we are going to see that, hey, this is not a very accurate model. But anyhow, well, that was it. And in terms of our calculation, this is what you conclude. Okay. Or you can say that human population grows, just faster than we expected, in short. All right. And example 6. Yes, this is a case that you are going to see decay. Okay. In which class, for example, if you are going to take calculus, regular calculus, that, well, you are going to do some physics or chemistry or mathematics, okay? You are going to see a lot of this type of problems. Well, but not in calculus 1, in calculus 2. Or on the other hand, probably you saw this one in pre-calculus also, okay? Suppose 800 grams of radioactive substance are present initially, and 2.5 years later, only 400 grams remain. So let's summarize this. Okay, present time was 800 grams of this radioactive substance. Well, 2.5 years later, how many grams? 400 grams are left. Okay. Determine the exponential equation that models this